Hi guys, so we're going to be taking a look at this summation right here and trying to find out what it tends to. And we're going to be doing it using a really cool method using contour integration. And so we're going to be trying to integrate this function right here. So f of z equals z all over e to the pi z plus 1 times e to the I pi z plus 1. I know this function seems completely random and out of the blue. It's so beautiful how everything kind of comes together at the end. Okay, so we have this function, and now what we're going to be trying to do is take a oh, contour integral of f of z around the contour c. Now, the contour c I will be writing down here. It's going to look like this. So I'm going to say this point here is r, and so we're going to be traveling from 0 to r, okay? And I'm going to call this point minus IR. So let me do that in black. So we have minus IR going down like that. And then we are going to go to the axis like this. And then we're going to go up. And yeah, so this is meant to be a square box right here. I don't know how much of a square box it looks like. But trust me, guys, it's meant to be a square box. Okay, awesome. So now this is our contour C. And what I'm going to do is I'm going to split up C into 4 different components. So I'm going to say C1, C2, C3, and C4. Okay, so basically parametrizing the contour C here. So now this integral, because we've parametrized the contour, we can write it as the individual integrals of each section. So we can integrate it on C1, dz, and then C2, dz, and then C3, and finally C4. Okay. One thing we have to always be careful of is poles in contour integration. Okay. So the poles are really going to screw us over, or they can be your best friends. Really depends how you treat them. And so let's find out what the poles are. And to work out what the poles are, what we simply do is set this bottom denominator equal to 0. So we find that either e to the pi z plus 1 can equal to 0, or e to the I pi z plus 1 can equal to 0. Okay. For the top case, we have e to the pi z equals minus 1. For the bottom case, we have e to the I pi z equals minus 1. Okay. And now, from our complex analysis knowledge, we know that e to the I pi times 2k plus 1 equals minus 1. So for the top one, we can just let z equal to I times 2k plus 1, right? So we can say z equals I times 2k plus 1 for k in the integers. Now for the bottom one, we already have an I. So we can just let z equal to 2k plus 1. And now instead of 2k plus 1, I'm going to use another parameter, 2m plus 1. And m is again in the integers. Okay. Okay, awesome. Now for the top poles, you guys can see how they lie on this top axis here, on the imaginary axis. So it's going to be I, 3i, 5i, 7i, so on and so forth. But those don't really matter to us. They're not on this red kind of contour that we have. So we don't really care about these top ones. Okay, we literally don't care about them. But the bottom ones, however, they are on our red kind of C1 section on the top. And they include points such as 1, 3, 5, 7, basically odd points. And this function here that we have has a contour at all of those odd points, essentially. We have a contour at all of these odd points, and we can't just plow through those contours in our little contour walk that we have here. We have to find a way to kind of go around them. Okay, so what we can kind of do is if I bring out our axes here, 0, this is R, and of course, I'm going to be letting R go to infinity, so that will come as well. Okay, so we have contours at isolated regions, and it's quite important why I said isolated, and we'll come back to that in a little bit of time. So I want to walk. As soon as I reach a contour, I just want to go around it like this. I don't want to go past it. And there's no way for me to go past those contours. So I just go around it like this. Around it, just like that, like that, like that, and so on and so forth. All the way to R, which is obviously going to be tending to infinity. Okay? And obviously this is the direction that's orientated. Okay? Okay, so this is what we have at the moment. And if I was to take a magnifying glass and kind of zoom in on this, what we will find is that if this is the pole in the middle, okay, what we'll find is that this kind of radius, which I'm going to call epsilon, I'm going to let that epsilon tend to 0. So these contours are very, very small. They are infinitesimally close to this pole right here, okay? So they're very, very small kind of contours that kind of help us go around the poles, which are blocking our way. So now we've kind of gone around our poles, and you may have a question. You guys may have a question. Why didn't I just go around a pole like this? Why didn't I do something like this? Why did I have to go above the pole, to get around it? Now, this question will be answered in just a second, but if you have that in mind, please do keep that in mind because we will be answering that in a second. Okay, so guys, we have all our regions sorted. We have everything sorted. We have our poles. We found a path around it. And so all we have to do now is use our secret weapon, which is Cauchy's residue theorem. And now what Cauchy's residue theorem says is that, so if I'm integrating an analytic function, okay, analytic function in some region A, let's say, with a few isolated singularities, okay, isolated singularities, around a closed contour C, then that is going to be equal to 2 pi I times the sum of the residues at the poles. Okay. So let me just label some important aspects of the theorem. Is that this is closed. So the contour is a closed loop. It is counterclockwise. So it's anti-clockwise essentially. So it's counterclockwise. Okay. Some more things are that F is analytic. Okay, great. And now this one, for the residues, the poles where you take the residues at have to be enclosed within the contour. Okay. I think now everything should start coming together. Okay. So, are the poles enclosed within the contour? Well, yes. Okay. And that is precisely why I went above the pole in each of these kind of odd regions here. And now, is it a closed loop? Well, yes. The contour C is a closed loop. Now, is it analytic? Well, you guys have to take my word for it. We don't have time to kind of prove that F is analytic, but I can assure you guys that this is analytic. Now, is it counterclockwise though? Well, not really, right? Because we're going in this region here, in that direction there, which is actually clockwise. Now that's not really a big of an issue because what we can do now is just to multiply that by -1, and now it should all make sense and work. Okay, and usually the counterclockwise direction is positively orientated, so that's why we multiply by -1 because we're in the clockwise direction now. Okay, so what we have at the moment is we have these four kind of integrals: C1 on C2 on C3 and on C4. And via Cauchy's residue theorem, we know that that is equal to minus 2 pi I times the sum of the residues, okay, at the poles. So now let's just kind of consider these three integrals here, okay? So imagine you're on a mini walk. You're on this region here, okay? You're on a mini walk. You have a device that tells you the value of f of z. Okay, you have a special device that tells you the value of f of z. Now, if you're on this line here, okay, which is essentially points r minus iy. Now, as r goes out to infinity, your device is going to get closer and closer to zero, because this term here is going to shoot off to infinity, which means f is going to come down to zero, essentially. Okay, so this region is not going to contribute anything, pretty much. And the same kind of logic can be used to argue that C3 doesn't account for anything, and C4 is also not going to contribute anything. Okay, so those integrals are essentially going to be zero. And use the same logic. Imagine you have a device, you're walking around the C3 bit, which is essentially the bottom kind of line here. And then imagine you're walking around the C4 bit, which is that sideways line there. And see what happens as r goes to infinity. Think about this function and see what happens as r goes to infinity. That's a mini challenge for you guys. So we know that this integral is going to be 0, this integral is 0, and this integral is 0. Okay, it's starting to look really, really nice at the moment. We have this integral right here. Now, that integral is done on the real axis. Okay, so it's done on the real axis, and we're going to let r go to infinity as well. So we're taking the limit as r goes to infinity, and it's on the real axis, okay, from 0 to r. So we only want the real component of f of z, dz, okay? And that's going to equal to minus 2 pi I times the sum of the residues. Okay, nice. It's looking really, really nice so far. Now, it's going to take, the video is going to be so long if I kind of go through each of this step here. So I'm going to give you guys that the residue, or the real part, sorry, of f of z is equal to x over e to the pi x plus 1. Okay, so pi just comes out of nowhere as usual. Okay, so awesome. Okay, so I'm just gonna keep this to one side, and what I'm gonna do is I'm gonna change this integral here, and I'm gonna, because it's done on the real kind of part of f of z, I'm gonna put infinity there. It's actually gonna be f of x dx. Okay, so just some nitpicking there. Okay, cool. So what we have now is this here, which we have to calculate, which is the sum of the residues. So to do that, let's do that right here. Let's just pick a point z0, which is 2m plus 1. Okay, so what we're trying to do is we're trying to find the residue at z equals z0 of f of z, which is equal to the limit as z goes to z0 of z minus z0 times f of z, okay? Which is equal to, now just to kind of simplify the writing that I have to do, I'm going to let this bit here equal to g of z, and this bit here equal to h of z, okay? So we have the limit as z goes to z0 of z times z minus z0 over g of z times h of z. So all I've done here, guys, is just replace f of z with this right here, okay, by putting g of z and h of z in the bottom. Now, we know that h of z naught equals 0, okay? I'm going to tell you guys that h dash of z naught does not equal to 0, and you guys can verify that. What this tells us is I can approximate h of z in a linear way. So I can say that h of z is just h dash of z naught times z minus z naught. Okay, so it's kind of like a Taylor series linear approximation thing going on here, but essentially you can do that. So now all we have is the limit as z goes to z naught of z times z minus z naught over g of z, okay, times h dash of z naught times z minus z naught. Okay, so you can see that these cancel out, and now this is equal to, well, z naught on the top, g of z naught on the bottom, and h dash of z naught in the bottom. Okay, so I know that h dash of z is I pi times e to the I pi z. So that means h dash of z naught is simply just minus I pi, okay? And g of z naught is just e to the 2m plus 1 times pi plus 1. Okay, awesome. So now we're ready to calculate the residue, which I'll write here. So I'll do it in this color right here. So the residue at z equals z naught of f of z is equal to z naught, which is on top, which is 2m plus 1, all divided by g of z naught, which is simply e to the 2m plus 1 pi plus 1, times h dash of z naught, which is minus I pi. So I'm going to put the minus here, minus here, and the I pi there. Okay, awesome. So just to kind of get some space, cut this out. Okay, so now if I was to substitute everything back into this here, what we have is we have the integral from 0 to infinity of the real component of f of x, or f of z actually it should be, but the real component of that is just x all divided by e to the pi x plus 1 from before dx, which is equal to minus 2 pi I times this, the sum of all the residues. So the sum of the residues is simply just going to be the sum of minus 2m plus 1 on top, okay, e to the 2m plus 1 pi, oh, I think I'm putting extra bracket there, plus 1, multiplied by I pi, and that goes from m is 0 to infinity, okay. So I'm multiplying this by minus 2 pi I, minus 2 pi I, the minuses cancel, and the I pi's cancel out as well. So all we're left with is 2 lots of the summation from m is 0 to infinity of 2m plus 1, all divided by e to the 2m plus 1 pi plus 1. And now just one final thing, if I divide by a half on both sides, we get exactly this via this beautiful approach that we took to form a real integral, which leads to the solution of the summation. Now, I'm not going to go through this in this video, maybe in the next video, but I'm going to give you guys that integral is equal to 1 over 24, which means this summation here is equal to 1 over 24. So this thing is equal to 1 over 24. And how beautiful was that, guys? Okay. Now, I probably will do another video explaining how I calculated that integral, because that's a video of its own. But it's just so beautiful how everything kind of came in together. And if you guys do have any questions, please let me know. I'd be happy to answer any questions about this. But yeah, I really hope you guys enjoyed this video, and I will see you guys in the next video.